Okay guys, thanks for joining me. This is my second revision sheet. If you haven't already had a chance to do these questions, I suggest you pause the video and give it a go now. I'm going to crack on and work through these. So this first question is a sector that's had a smaller sector taken away from it. Okay, so I'm going to think of this question as having a small sector of a radius of r, and then a bigger sector over the top of that, which would have a radius of 2r, because it's double it. Okay, so I like labeling my smallest thing r. I imagine a lot of people possibly did this question using a big R and then like half of r. I'm going to avoid the fractions where I can. So I've been told the area is double its perimeter, so you have to multiply the perimeter by 2 to get the area. So that straight away gives me somewhere nice and easy to start in that I want to find an expression for the perimeter of this blue shape and an expression for the area of this blue shape. Okay, so I'm already thinking about sectors. I'm going to need my arc length. Let's come over here and say, well, we need arc length, which is equal to theta times r, and we're going to need our area, which is equal to theta over 2r squared. Okay, I'm just going to need to apply those formulas, first for the perimeter and then for the area. So the perimeter of this blue shape, to begin with, I've got these two side lengths here. Okay, well, if you look at this diagram, that's just my bigger radius subtract my smaller radius, which is just going to be r. So each of these are r. And then I'm going to be adding those two together, so I have 2r. Okay, applying my arc length formula on my bigger arc. So now I'm thinking about this distance here, which is this distance here, which is theta times r. So that's going to be a third times 2r. That's 2 over 3r. And then I need, of course, my final distance, which is the smaller arc length, which is the arc length of the smaller sector, which is going to be theta times r, which is a third r. So that gives me a third r plus a third r. Add those together, my perimeter is equal to 3r. Okay, I'm now going to do something very similar but with my area. So if I'm looking for an area of a shape that's had a shape taken away, I'm going to think of doing my bigger area first. So that's theta over 2 times r squared. Now I need to be careful because that's 2r all squared. And actually I know theta, don't I? 1 over 3. Okay, so that's an expression for my larger area. Okay, that's this whole sector. I want to be able to subtract this bottom sector from that. So now I need to minus, again, use my area of a sector formula, theta over 2. It's 1 over 3 over 2 r squared. Now r for the smaller one is just singular r. Okay, well, working this out, I have a third over 2, which is 6th times 2 squared, which is 4. I have 4/6 r squared, which would obviously simplify. And here I have minus 1/6 of r squared. That comes out nicely to a half of r squared. Okay. So now I have an expression for my perimeter, an expression for my area, so I can go ahead and sub those two things into my original equation at the top. Okay, I'm going to do that down in this bottom right side. So my area is 1 over 2 r squared. That's equal to 2 times my perimeter. That's going to be 6r. Okay. So I want to solve this. I'm going to times both sides by 2. Get r squared equals 12r. If I subtract, it's going to give me a quadratic. Minus 12r equals 0. Okay, well I can factorise an r out of this. It's a nice easy quadratic to solve. So that leads me to r equals 0 or r equals 12. Okay, I know r doesn't equal 0, so I'm going to go ahead and say r does not equal 0, just because of the nature of the question. So r is equal to 12. Make sure you read the question. Given its area to double its perimeter, find its perimeter. So I'm looking for the perimeter of this blue shape. Well, we found that earlier. That's 3r. So P is equal to 3r, which is 3 times 12, which is obviously 36. Question 2. Been given the equation of some quadratic. We know it has no real roots. We've been asked to sketch this and label its intersection. Okay, so A here. We've also been told k is greater than 0, so we can think about the implications that has when we're sketching. Okay, so I know it has a positive intercept, so it's going to intercept at 1. I'm also thinking about the fact it has no real roots. So I know it's not going to cross my x-axis. I also can quickly think about kind of completing the square, just because I want to make sure I put the minimum on the right side. Okay, if I was going to complete the square on that, I would say that that comes out as x plus 2k all squared minus 4k squared plus 1. Well, that turning point then, my turning point is going to be equal to minus 2k and then 1 minus 16k squared. So my turning point's on the left hand side, so I'm going to have something like this. I know that point there is 1, and I know my turning point is minus 2k, 1 minus 16k squared. Okay, so that's part A. Part B, find the range of values of k. So I know that k is positive, okay, because it's greater than 0. I also know that this quadratic has no real roots. Well, if the quadratic has no real roots, I know that b squared minus 4ac must be less than 0. I know that I want b is 4k, so I've got 4k all squared minus 4. A is 1, C is 1, so 4 times 1 times 1 is 4. Okay, so 16k squared minus 4 is less than 0. Leads me to 4k squared minus 1 is less than 0. Factorising that, 2k minus 1, 2k plus 1 is less than 0, just from difference to 2 squares, which leads me nicely to the inequality that k must be between a half and minus a half. It's tempting to give that as the answer. However, I think you've just got to be careful here and consider the question as a whole. we already know this about k. We already know k is greater than 0. So the discriminant has told us k has to be between -half and 1/2. However, we know that k is greater than 0, which leads us to 0 is less than k, which is less than 1/2. Okay, I imagine it's quite a common mistake on these kind of questions, that people would forget the 0 there and leave -1/2. Be careful. Okay, question 3. Solve this exponential in exact form. Okay, I hope we kind of recognize the quadratic form here. Okay, we have some exponential squared. Okay, I'm going to rethink of e to the 2x as e to the x squared, using our laws of indices there to bring it out as a bracket. Okay, and for a minute, I don't normally like writing in extra variables when I don't need to, but you'll see a lot of people do this. Replace e to the x with some other variable, and realise that that equation looks a bit like this equation here. Okay, so I'm thinking about just some quadratic with variables 1, 4 and -12. Sorry, coefficients 1, 4 and -12. And can I factorise that? So I don't like using a dumb variable, like I said. A lot of people will. I'm happy just putting e to the x's in here. Okay, well, two numbers are going to multiply to make -12. Add in this case to make 4, because this coefficient at the front is 1. Okay, it's going to be -6, +6, -2. Okay, well, that would lead me to believe that e to the x is equal to 2, or e to the x is equal to -6. Obviously, if we think of an exponential curve, it's always above the x-axis for just e to the x, so it's never going to be equal to -6. I'm just going to recognise that. Okay, I tend to still deal with that bracket and write something down, but write down a not equals, because it doesn't provide any solutions. So e to the x equals 6, logging both sides, x equals ln2. Okay, question 4. Find the limit of a recurrence relationship. Now, this is a question that's really, really easy, but people always forget how to do it. It doesn't come up very often. So I think the first thing to understand is what a recurrence relationship is and why that would have a limit, what a limit means. So a recurrence relationship, you're putting some number in. Okay, we have an input, and you're running some process on it and you get an output. Okay, so just imagine some numbers going in. 10 goes in, 48 comes out. Then you stick 48 in, another number comes out. Okay, so a limit of something like this, when would that process stop? Well, that process would only ever stop if your input suddenly become equal to your output. Because if your input and output were equal, you would put in the same input again. Okay, we're just looking for the point at which, when do you keep putting numbers in and it gets stuck? It just keeps churning out the same number. Okay, well, that's going to happen when those two things are equal. So all we tend to do is we just let each of them equal L. Substitute that in. L equals 5L minus 2. Okay, so 2 equals 4. L equals 1/2. Okay, the limit of that recurrence relationship is 1/2. Okay, that doesn't mean that recurrence relationship will always get to 1/2. Just means if you hit 1/2, it's going to get stuck there. Okay, you put 1/2 in, 1/2 comes back out. Okay, and you can see that quite quickly. 5 times 1/2 is 2.5. Subtract 2 is 1/2. Sub 1/2 back in, you'll be in the same position still. Question 5. So we've been given some expression. I've been asked to use Newton-Raphson, which is a formula in your formula book if you don't already know it. You do need to be working with a function though, and we do like that function to equal 0. So I'm just going to go ahead and kind of define a function. So an f of x equals, and if I need a 0 on here, I actually need to subtract that too. So e to the x sine 2x plus 1 minus 2. Okay. For Newton-Raphson, you need to be able to differentiate your function. So I'm going to go ahead now and differentiate this. Okay, we're e to the x sine x. I've got two things being multiplied together. That's going to be product rule. Okay, so first, again, product rule, I think I said last week, is something when you start doing, I wouldn't waste time writing U's and V's. I would just get into that process quickly. Two things multiplied together, differentiate one of them, leave the other one the same, and then reverse that. Differentiate the other one, leave the first one the same. Okay, so e to the x differentiated is e to the x. Leave sine x how it is. Sine 2x plus 1. Okay, now do that the other way around. Leave e to the x how it is. Differentiate sine x, or sine x becomes cos x. There is a function inside this bracket, so I need to remember a bit of chain rule. My derivative's going to pop out. Okay, I'm just thinking about the fact when I differentiate sine 2x plus 1, I actually get 2 cos 2x plus 1, where the derivative of this bracket is popped out. Okay, so e to the x multiplied by 2 cos 2x plus 1 minus 2, differentiate minus 2, still minus 2. So I have what I need. I've got my function. I've got my derivative of my function. It's giving me a range for alpha. Okay, so with Newton-Raphson, you need a start point. You need an x0. I'm just going to go ahead and set that at 2.5, just in the middle of where I know alpha could be. And then with Newton-Raphson, to find your next iteration, you do your iteration before minus f of your iteration before over f dash of your iteration before. Okay, and then you repeat that a few times to get your different f values. I'm going to use this calculator. So x0 is my answer before, so I just want to set 2.5 as my previous answer. Okay, so I wanted to be able to set this up so I can just press equals and do this iteratively. So for each new iteration, I want my previous answer minus f of my previous answer. So f is e to your previous answer multiplied by sine 2 times your previous answer plus 1 all minus 2, and my f dash is e to my previous answer multiplied by sine 2 of my previous answers plus 1 plus e to my previous answer multiplied by 2. I'm going to put that 2 here, cos of 2 of my previous answer plus 1. Okay, now this question hasn't said anywhere whether it's doing degrees or radians. My calculator's already in radians, but it is worth thinking about. And while it hasn't told you, there is a reason we know this must be radians. Okay, whenever a question contains differentiation or integration, you're not going to be asked to do that in degrees. Okay, they don't really have to state it's radians. As soon as you're differentiating, it has to be radians. Okay, so happy with my calculator in radians. If I press equals, I get an x1 of 2.770 because it wants it in 3 decimal places. I would realise it's only asked for the root, so I'm just going to iterate until I'm confident that these values aren't changing. Also, having set my calculator up using answer, I don't have to keep typing in. Okay, so x2, I can just press equals again, and you get 2.711 equals x3 equals 2.708. Okay, and that one didn't change at 3 decimal places. It changed further down. If I press equals a bunch of time, I can see that's converged to this value. So I'm happy that my root is 2.708 to 3 decimal places. Question 6. Find the turning points of this in exact form. Okay, so for turning points of a curve, I know I want the derivative to be 0. So I know I need my derivative. When I look at this expression, I see that I have 2 things being multiplied together. So immediately I'm thinking product rule. Differentiate the first thing. ETX stays the same, so it's just ETX. Leaves the second term alone. Then reverse that. Differentiate the second thing, which is 4x minus 1. Leave the first term alone, e to the x. I want to find when my derivative is 0, which are going to be my turning points. So 0 is equal to, both these terms have an e to the x in, so I'm just going to factorise that out. And then I can collect like terms in these 2 brackets. I have 2x squared. I have minus x plus 4x, which is 3x. 1 minus 1, which is 0. Okay, now this is quite nice. I can factorise this a little further. 0 equals e to the x, and x could come out that bracket, leaving me 2x plus 3. Okay, so I have 3 factors multiplied to make 0. So I know this is true when any of those factors equals 0. Okay, well, one of these is quite nice, which is my e to the x, because e to the x is never 0, so I can eliminate that. That's not going to provide any solutions. My second one's already solved, x equals 0, and this last one leads me to x equals minus 3 over 2. Okay, so I now have my x coordinates of my turning points. I can substitute those into my y equals to find my y values. Okay, so y is equal to, it was e to the x. Let's say what we're subbing in. When x equals 0. Okay, let's substitute 0 in here. Y equals e to the 0 times 2 0 squared minus 0 plus 1. Okay, just substituting back into this original expression, which e to the 0 is 1. That bracket comes out as 1. That's just 1. I also have when x equals minus 3 over 2. Y equals e to the minus 3 over 2. 2 minus 3 over 2 squared minus 3 over 2 plus 1. Now this one I'm going to jump to my calculator for, although because I want it exact, I'm going to ignore the e to the minus 3 over 2 at the start. And just compute that bracket. So I've got 2 lots minus 3 divided by 2 squared minus 3 divided by 2 plus 1, which gives me 7. So y equals 7 e to the minus 3 over 2. Okay, so to answer the question, my turning points are 0, 1, and minus 3 over 2, 7 e to the minus 3 over 2. Question 7. The region R is enclosed by the x-axis, the y-axis, x equals 2, and some curve. Okay, so it's worth looking at this curve and realising that between my x's 0 and 2, it strikes me quite apparent that that's always going to be positive. Okay, e to the x is always greater than 0 between 0 and 2, as is x squared. Okay, so it's an integration question because it's an area, but I don't have to worry about it dipping below the axis. Okay, I would think about that. In some questions you might, if I was trying to do some integral that, I don't know, did something like this, I was looking for that area. Okay, you do need to be careful and think about the fact that this area comes out negative. Okay, so this is definitely part of my thought process in this question. However, you can quickly arrive at the conclusion it is all positive, which is important. Okay, so that question is essentially asking you to integrate between 0 and 2 x squared e to the x dx. Okay, so two things being multiplied together is integration by parts often. Okay, I think that's going to be helpful in this question. Integration by parts, I start by labelling u, labelling v dash. So my two things being multiplied together. And I normally go with u being the thing that gets simpler when you differentiate it. Okay, so in this question, I'd never pick e to the x because it never gets simpler. E to the x is always going to stay the same. So my u is going to be x squared. So leaves me to u dash being 2x. And my v dash is e to the x. Integrating that gives me v is e to the x. Okay, well, by parts is u v minus the integral of v u dash dx. Okay, so just applying that here. I've said y equals that integral, that doesn't. My r is equal to, the area I'm looking for is equal to that. So applying that formula here, I can say, well, r equals uv, which is x squared e to the x minus the integral of vu dash. So that's going to be 2x e to the x dx. Okay, so the whole point in integration by parts is hopefully your new integral is easier to integrate than what you had previously. In this case, it kind of is. We've gone from having an x squared to just an x term, so that feels a bit simpler. We do, however, still have two terms being multiplied together, so this question is actually repeated integration by parts. Okay, some people will use different variables here. I'm kind of happy like labelling u and v, knowing I'm talking about that bit, and then labelling u and v again, knowing that I'm talking about this new integral I'm looking at here. So I'm now just thinking about this integral here by parts again. I've got 2x and I've got e to the x. Well, 2x would get simpler if I differentiate it. So u is 2x, u dash is 2. V dash is e to the x, integrating is e to the x, and applying my formula again. Now, the most common thing I see wrong here is we're doing by parts again, using this information here, but that just applies to this integral. So I see a lot of people get that minus in there wrong. Okay, how I kind of deal with this is I lay out what we have so far. So far we have x squared e to the x minus, and then I just use a bracket, say we're doing by parts again. Okay, well, we're doing by parts again. So now I can think about this formula here with this information going into some square bracket. Okay, so uv is 2x e to the x minus the integral of v u dash. So v is e to the x, u dash is 2, which is 2 e to the x dx, close that square bracket. Okay, so now I would expand that bracket. I have x squared e to the x minus 2x e to the x minus minus, so I have plus the integral of 2e to the x dx. Now this is a nice place to be because the integral I've landed on it suddenly just has one kind of algebraic term that I can integrate on its own. So x squared e to the x minus 2x e to the x plus 2 e to the x. Feels like I'm finished. I've just got to bear in mind that actually right at the top I had some bounds. Okay, it's not unnormal that you'll drop bounds while you're doing by parts, but you've got to remember to pick them back up. So I'm looking at this between 0 and 2. And I want to sub them in to find some value. It's asked for it in a form, so I can't just type this into my calculator. Okay, substituting 2 in. So x squared is 4e to the 2 minus 2 times 2, which is 4e to the 2 plus 2e to the 2. Okay, so that's from substituting the 2 in, and I want to subtract everything when I substitute the 0 in. So 0 squared times e to the x is 0, minus 2 times 0, e to the 0 is 0, and then I have 2e to the 0, okay, which won't be 0 because e to the 0 is 1. So look at my first three terms. First two cancel each other out. I've got 2e to the 2 minus 2. Okay, question 8. Find a general solution to this differential equation. So differential equations, I'm going to want to collect my variables on the right side. So I'm going to divide through by x, get 1 over x dx dt equals 1 over t plus 1. Okay, just thinking about whatever variables up here, I want to collect them terms over that side. And then to go from differential equation to normal equation, I need to integrate both sides. Okay, so I'm integrating 1 over x dx, and that's going to be equal to my integral of 1 over t plus 1. Okay, now my one on the left hand side's fairly standard. That's the integral of 1 over x is ln x. This integral's a little bit more difficult. 1 over t times t plus 1. What I would like to do is just deal with 1 over t plus 1 to one side. And realise that that can be partial fractions. Okay, as soon as I've got factors on my denominator, I would definitely take time to think about the fact that this might be easier if I can split it into partial fractions. Multiplying through by my two factors, it's going to give 1 equal to a times t plus 1 plus b times t. Okay, I'm going to let t equals 0. This gives me a equals 1 quite quickly, that's nice. I'm also going to let t equal minus 1. Okay, which is going to give me 1 equals minus b, which is b equals minus 1. Okay, so I can take this integral, and actually I can split it into the integral of 1 over t minus the integral, 1 over t dt minus the integral of 1 over t plus 1 dt. Okay, whenever I've got an addition or subtraction in integral, I quite often like to split it into two separate integrals. In this case, that minus there is just because my b is minus 1. Okay, so ln x equals 1 over t integrates to ln t minus ln t plus 1. Okay, I don't need to worry about bringing any factor out, okay? My thought process here is, does my denominator differentiate to get my numerator? Okay, well, if you can differentiate your denominator to get your numerator, it's going to go to a log. In this case, it does that without playing with a factor. Okay, I am going to have to put plus c here because I've done some integration. There's some constant that's unknown, and that's why we've got a general solution, because there's some unknown in this. I'm going to go ahead and say ln x equals ln t over t plus 1. I'm going to also recognise that I can, with plus c, because it's just a constant, I could write that as some log. So I'm going to write ln a, which leads me to ln x equals ln a times t plus 1. And now it's tempting to remove my log, so I could exponent both sides and say x equals a multiplied by t over t plus 1.
So if you've made it this far, great work. Well done doing the sheet. There's another one available now on my Twitter. Again, same time next week, I'll be posting the solutions up on YouTube. Keep up the good work. Thanks very much.